last talk before the lunch break, it is about self-driving cars and more specifically what deep learning can and cannot do. And I would like to welcome Professor Dr. Wolfram Burgard. He's the founding chair of the Department of Engineering and professor of AI and robotics at the University of Technology at Nuremberg. So, welcome.
Thanks. Thank you. Thanks for coming, and hopefully you're going to stay until the end and not run out of this room. Right? So I was asked to basically talk about deep learning and what it can do and what it cannot do. And we as scientists, we are always getting asked about this. And what I can tell you in the end, I won't give you a definite answer. But what I want to do is I want to improve your understanding about where we are and where I think we are going to. And if you look at self-driving cars, and this is an example of a typical software stack that, or a rough software stack with some core modules in there, but the most important ones when it comes to the actual functionality, namely staying on the road, not hitting anything, and not getting hit. And this is what basically an autonomous car needs to do. And in these components, there are a few ones that are supported more or less by certain type of, or by certain technology that has been come out of the big field of robotics and artificial intelligence over the past 10 to 15 or maybe even 20 years. And the first one is what is called the probabilistic paradigm, that started in the around 95 of the last century, where people actually were thinking about this question of how can we actually better interpret the data, get better like object recognition, how can we build maps, which is particularly popular in robotics, and we will see an example later on. And how can we actually localize the robot? And those two functionalities are super important for this functionality that I mentioned before, namely staying on the road. Once a vehicle knows where it is in the world, it can easily just stay on the road and not go onto the curb and things like that. And starting from there, like for mapping, we basically built maps that are used in localization. We also use probabilistic methods for predicting what is going to happen in the world. For planning, I'm basically taking uncertainty into account in the planning process and also in control, like where people actually thought about uncertainty intervals in control regimes. And that made the car, or brought us to a certain level of robustness in autonomous driving. But then there came this revolution of deep learning and deep models, and all of a sudden, like most of the sensor interpretation stuff that we had been doing with probabilistic methods was blown away by so super robust methods that we also saw in the previous 2 or 3 talks. Although being robust in this context, there are a few deficiencies there as well, right? So they are not as good as in the context of mapping. Localization is not as robust based on deep methods. In prediction, they're getting better and better, and actually my perception is that they're right now outperforming that we have been doing in this context of probabilistic robotics. And they're also like slowly getting into planning and control. For example, in planning, when it comes to complex decision making, for example, this question of should I answer the intersection or not, like if it's a keep clear zone, that is a typically hard decision, which is hard to program, and this is why it is way better suited for learning than for hard coding. So probabilistic localization, and people like this term AI goes so quickly over the tongue, right? That basically behind AI is a lot of math, and that's why I always show an equation. And this is the equation underlying probabilistic localization. And when you think about self-driving cars, like every car has an implementation of this equation for estimating its pose on the road. And I can show you an example of this, like being run on a robot. Well, basically what these systems have, they have some sort of a map, and we are going to talk about this in a few seconds. And trying to match the sensor measurements that they have, in this case ultrasound, relative or with respect to the map, and doing this over time, and then trying to figure out where the vehicle actually is. And you can do this with an enormous accuracy. That is basically what you can see here in a qualitative way, with a robot trying to actually go to the very same spot in this blue dark, or this black stripe on the ground is just for illustration purposes. The robot uses its onboard sensors and the map to trying to figure out where it is. And you can nowadays do this in a millimeter range. Right? So when you think about production, then this type of technology brings you extremely far by being able to deploy vehicles that are almost deterministic in their navigation capability, so which is pretty amazing. And you can also do this in self-driving cars, and this is an example implementation that we did a few years ago, where we basically implemented this type of valet parking in a GPS-confined area, where we basically used a map that you can see on the top right, a high-density map. It's a 3D model of this parking garage to basically localize the vehicle. And these maps are super useful for planning, trying to find the optimal trajectory for the vehicle, and then you can also localize the vehicle inside this parking structure and then go up to the roof and park the vehicle over there in an autonomous fashion. So this is what has been done substantially in this field of probabilistic robotics. There's also companies that came out of this, and this is a startup that I founded together with some of my students called Dotscene. And what we are doing is we're basically building highly accurate 3D models of real estate. Not only real estate, we also use cultural heritage objects. We are one of the most accurate models of the Leaning Tower in Pisa, and this what you see here is the most accurate model, 3D model of the cathedral in Freiburg, Germany. And it's not only an outdoors or an outside model, but it's also indoors, outdoors, and you can use this for all kinds of purposes in the context of real estate, even like controlling the modifications in buildings that typically happen in cities when people add additional stories to buildings and so on and so forth. And this technology is really ripe for the market right now. But when it comes to autonomous driving, it also complicates our lives. And because the crucial aspect in self-driving cars is this thing on the top right corner here, namely the map. This question of how can we get this map and how can we maintain it? And the reason for this is that usually the information that you need is not only geometric, that what we saw in the previous examples, where you just have a 3D point cloud or a 3D mesh. You also do need some semantic annotations there. Right? And here's an example on the top right corner. You basically see one typical HD map being used in self-driving cars, where you see not only lampposts as unique and easily to store features, but also lane markings and so on and so forth that are used for localization. On the bottom left, you see an intersection and what the typical map operations teams do with these maps in order to facilitate navigation through intersection. One of the hardest problems there is this question of which traffic light is associated to my lane, right? And this is an extremely difficult question in this context. And currently, this is eased by the map operations teams, basically by drawing or putting all the light bulbs basically into the map, so that the vehicle exactly knows where it is. It can directly infer which traffic light is associated to the lane it is going through. Right? And also the topology of the intersection is there, because typically it's hard for an autonomous vehicle to basically tell how to go through an intersection. And then on the right-hand bottom side, you see something like a ground 3D map, which is super useful. I do not know what they exactly are using it for. It's from Waymo, but my prediction is that they are using this to subtract the ground points from the perception, so that you can easily get the objects in the environment. Right? It basically facilitates perception in this case. So although this is super powerful, right, and it brings us very, very far, at the same time, right, it's super expensive. Building these maps is extremely expensive. You also need to assume that all the features that you have in the map are available. And if you look at the top right video, which has been recorded from one of my colleagues, Ryan Eustace in Michigan, Ann Arbor, then you see that there are certain conditions where important features like lane markings all of a sudden disappear, which makes it extremely hard for a vehicle to actually localize itself. And this is where this technology of using maps for localization breaks. Right? And we need to find a way to resolve this. And so one option for this is change detection. I will briefly talk about this as well. Then also domain adaptation. Think about the case where you drive at night. I think the world is going to look completely different. And at the same time, these maps are extremely difficult or expensive to update. And finally, they are also a barrier to level 5 because it's close to impossible to build such expensive maps for the entire world. So in a GPS-confined space, it might be easy, but for the entire world, it's basically too expensive. And on the other hand, like slight changes in the map might, doesn't mean that a change needs to be big. So in the bottom of this picture, you see a slight modification where people put just 3 cones into on the lane markings between 2 lanes, and all of a sudden this change confuses the vehicle so much that it cannot go anymore. Right? So there's a famous video on YouTube about this actually. So change detection is an important aspect as well, and the question is how to do this. And usually when you think about this paradigm of having these autonomous vehicles with expensive sensors, then all of a sudden you realize that going there every day and checking as to whether the world is the same as yesterday is extremely expensive and therefore probably not a viable way to go. And the only solution would be to basically crowdsource things. As long as we live in this space of mixed traffic where we have human-driven vehicles and autonomous vehicles, we could potentially use the human-driven vehicles to monitor changes. And this is the crowdsourcing data that BMW recorded on one day in US and Germany, or in Europe, and you can basically see the density data of where vehicles have been during this day. And in fact, you could think about this question of can we leverage this data to perform change detection and then only go to these places where potential changes have been done. Problem is these vehicles, like these consumer vehicles, don't have all the expensive sensor data, so you need to be able to do this with cheaper sensors. And how can you do this? And so here what we did is trying to identify spatial changes in the road layout based on the vehicle data that come from odometry or IMUs in the vehicle and vision, for example, and compared this to the HD information stored in the maps. And this is here a visualization of the data that we were using. You basically estimate all the lane markings and the trajectory of the vehicle, and then trying to figure out as to whenever there's a construction site and the vehicle has to deviate in some direction to actually try to estimate as to whether this is a real construction site or this is just an estimation error. And you can, in fact, do this. Right? It's not simple. You can do it just like with one observation currently. We'll talk about this in a few seconds. Right? But in this case, what we did is we basically took the idea of crowdsourcing and took the votes of many, many vehicles traversing this place and basically voting on as to whether there is a change or not. And then you can take a majority vote where you have a user-defined threshold to actually identify as to whether this is a construction site or not. And applications for this look like this over here on the right-hand side. You basically see how green means no change, red means change, how as the more the vehicles go into this construction site, the higher the likelihood of that there is actually is a change in the map. And some vehicle has to go there and to remap this. Or potentially you could also do this in this case with the onboard information coming from the crowdsourced data. And here in this slide, you can see that the right figure indicates that the more data you have, the better you get at estimating the fact that there's a construction. Right? But the general limit or the general problematic with this is, while this seems to work, right, in the end, you want to be able to not only use or rely on hundreds or thousands of vehicle data, but potentially do this with just one observation. Right? I regard this somehow as a slider. The more performant you become with this, right? If you are able to estimate this with just one observation, right, then you basically reach this limit where you say, yes, this is the optimum that you can have. But if you can update the map with just one observation, then the question is as to whether you overall need a map anymore. Right? So this is kind of like a place where we are right now and where deep learning basically kicks in. Right? So we have seen limitations of deep learning, but at the same time, I think with deep learning, we will more and more able to actually shift the slider to the left and use fewer observations to basically update the maps on the fly. And here are a few examples of things that we have been working on, like semantics, basically trying to understand the world is one of the things that we need to do, like, is this a construction site or not? And if there is a construction site, then it's higher the likelihood is higher that actually the lanes have been changed. And the vehicle needs to trust potentially other information like the yellow markings to perform the navigation task. And there are different ways of understanding semantics here. And this one is the so-called panoptic segmentation, which is basically able to reason about instances and amorphous regions or just stuff around. So as to what is a road, for example, and what is a sidewalk, plants, trees. Again, like AI is not easy, right? This is a model that you need to build in order to cope with the state of the art or advance the state of the art, and it takes a lot of effort to do this, just to let you know. And then once you do this, right, then you can get models that actually perform or are highly performant, achieve the state of the art. Here what you can see is panoptic segmentation based on LiDAR. And when you carefully look at the video, you see that in some cases, in the previous video, it was more apparent that the color of the vehicles changes based on over time, which means that the car doesn't exactly know that the vehicle that it sees in this frame is the same that it saw in the previous frame, which brings us to the fact of panoptic tracking. And again, I don't show you the network, it's even more complicated, but with this you can basically then also make inferences or temporal inferences and track objects over time, which is extremely important for prediction. And the hope is that with these deep models, we will at some point in time, and some we are already, be more performant than with the state-of-the-art probabilistic approaches. And just to skip this briefly and show you one of the results that you can obtain with state-of-the-art techniques. So with this small truck there you see a color change. So this is a case where the model actually makes a mistake. And I think that state-of-the-art probabilistic methods would probably be better at that. But we're getting there. Right? So, and deep models over the long time are going to surpass these probabilistic methods, which have been handcrafted, designed for a long period of time, and also involved learning as well. But the robustness of these deep learning methods is simply so promising that I believe that they will surpass also the probabilistic approaches. There's also this problem of domain adaptation. Most autonomous cars are tested in sunny and dry spaces. They would not be able to drive in rainy Amsterdam. But also they would probably have problems at night. And so on the left-hand side, you see a typical night image. And labeling night images is a nightmare. Right? So because you basically have a set of dark pixels, and you want to know what is this dark pixel. Right? Is this a tree or a person? And so it's close to impossible. And this is why it is so important to also reason about and think about ways to improve the efficiency of labeling processes. And this is where domain shift techniques come into the game. And this is where we, for example, used infrared cameras to basically, which have a lower domain shift between day and night, and then use those to train a network. And in the end, having a RGB, a camera-based system to be more robust even in dark scenarios. HeatNet, it's what it's called. And here you can see some of the performance, like in this bottom, you see the teacher network, which actually performs pretty bad in the night domain, but with the T domain, if you have the thermal data, you can get much better. The interesting aspect is this here over here. Let me see whether it is here over here, because this is just an RGB network trained or supervised by the thermal images on the nighttime domain, and you can see that the performance is actually pretty accurate. So skip this and then go to the very end and briefly talk about where we are, for example, with predicting intersection or topology of roads, which is super important. Right now, as I mentioned, these maps are typically handcrafted, and the vehicles know from manual annotation where to go. And this is an extremely difficult problem. Like looking at an intersection some of we humans, we can do this. We arrive at an intersection and we know in which lane we need to go. Not in all cases, but we are pretty robust with that. But autonomous cars are extremely bad at that if they don't have an HD map. And this is why we started looking into this problem, basically making predictions about the topology. And this is a so-called lane graph net that we developed. And here you can see some of the predictions that it currently does. It is good on straight roads, which is actually easy, but I can tell you it's terrible on intersections, and that's why we are still working on this. And which also should give you an idea that while we often speak about AI and we sometimes give people the impression, oh, you only need to throw AI at this and then it's going to be solved. No, they are really hard problems, and it takes a lot of effort in some cases to solve them. And with this, I'm done. I just want to let you know that currently still we have like probabilistic and deep learning approaches. We are far away from end-to-end driving. Right? It's going to take a while doing this with deep networks. Although I truly think that deep networks will support more and more tasks in the future, and they will be basically the major source for advancing the state of the art. With this, I'm done. Thank you for coming, and thank you for listening.
Thank you so much. Excellent. I'm sure we're going to have a lot of questions shortly, so let's get started. Yes.
Thanks for the talk. That's what he said.
We keep trying to make the cars smarter and smarter, and there's been great developments. There's still a lot of challenges. But the transport infrastructure is still dumb. It's bitumen, it's line markings, it's lights. So why has there not been some more focus, especially now with IoT and smart cities and various things, on making smarter transport infrastructure that can interact with the vehicles?
That's a good point, and I think in the long run that might happen, right? So, I think if you look at cities, right, cities have been built for cars, right? I mean, all the roads, all the parking spaces, and I think this might change in the future as well. As soon as this like self-driving capability becomes a commodity, right? So at that point in time, where we reach this level that self-driving cars are a real business, then cities will also start changing and facilitating this and make self-driving cars more effective. Right?
Very nice talk. I'm just wondering, you mentioned probabilistic, models, and you also mentioned deep learning. Have you considered Bayesian machine learning methods such as like stochastic rate averages? And then the other second question is, for your heat net, do you actually also include LiDAR in it for the comparisons that you show?
Thanks for these questions. First of all, yes, in fact, we also look at probabilistic deep networks, and this is also a very cool space. In particular, when you think about, for example, localization. I mean, localization typically means that you do have probabilistic models for the actuators and the sensors. And this is where deep learning can kick in, because the problem there is typically the independence assumption that you have in this like Bayesian formulation. At some point in time, you typically make independence assumptions, and these deep networks can way better cope with these or with violations of these assumptions. And this is why these Bayesian machine learning techniques or deep learning techniques are so powerful in this domain. People haven't really used them in practice, but we started with this, and results look promising. So I'm optimistic that even there, like we will, like I used to say machine learning and deep learning is kind of like a virus, right? So whatever problem you have, right, that like before starting to engineer it and before you start tweaking a threshold, start thinking about how to learn it and how to use a machine learning model right in there. The second question was regarding
LiDAR.
LiDAR. No, in the HeatNet, this was just vision and infrared or thermal.
First of all, thank you for the outstanding talk. My question is, nowadays, every car solves the problem by themselves, right? Like, I drive in front of you, my car has to solve the problem. You're behind me, you have to solve it again. This gentleman behind you has to solve it again. Can't we use some sort of, or what are your thoughts on linking these cars up and having them solve the problem together and learning from each other?
That's a very, very good point. I think that not only affects self-driving cars, it also affects robotics, for example. And there's a few things that we should do in the future and that should be done more. And one is learning from humans. That's in particular important when you think about the way how to instruct robots for doing certain tasks, but it could also be like adapting to the user, right? So, I mean, when you sit in a self-driving car, I don't know as to whether you have ever done this, they are very, very good, but at some cases you actually think I would do this differently. And this question is basically unsolved and not addressed at all, right? So learning from users is a super important task. And the next one is fleet learning, right? And this is something that has been looked at also not very much. I mean, this stuff of like the crowdsourcing, it goes into that direction, but in principle, this is the way to go, right? That we need to have mechanisms to learn from large scale, like fleet data, and improve models based on that, together with incremental learning, right? So this idea of restarting the learning process with every single image that comes in, that is not very sustainable. Yeah. Thanks for this question.
Hi, thank you for the very interesting talk. I'm sure you're familiar also with the works of Comma AI, and I think you've demonstrated quite dramatically how difficult it is to go down that route of feature engineering, maintaining maps, and then doing the planning. You said end-to-end driving of cars is maybe pretty far away. Comma AI has already released some videos where they actually test drive in end-to-end mode with that little device on the screen. It looked quite impressive. So my question is, do you think that self-driving, like full autonomy, is solvable going down the route of trying to extract features, or will it just in the end be end-to-end learning?
That's a good question. I think this entire space of, or this entire task of feature engineering, that will go away. Because you know, if you think about these domain shifts, for example, right, or like exceptions, right, that is not solvable manually, and we also need to find a way to get from supervised to basically self-supervised or unsupervised. So I think this is a direction to go in the perception space. And then I like videos about end-to-end autonomous driving as well, but we all should know that these are just existence proofs, you know, in the sense of, yes, it has been possible on that particular day, at that particular hour, in this particular traffic. But there's no way that these videos and demonstrations tell us in which way this generalizes. And this is something that we actually need to look into. And I think that this idea of like slowly introducing more and more machine learning into these models, into the existing pipelines, makes more sense than just throwing one big network at it and then hoping that it's going to work.
Good. We have one more question.
Hi, amazing talk, by the way. So my question is, to what extent would the robot understand that the environment is not safe anymore? Perhaps if there's ice on the ground or something, for the passenger to not feel safe anymore, what would it do then?
That's a good question. And to be honest, there is very little research on this as well. I mean, when you come with this, or when you come with this big data argument and basically say, you only need to record data when the road is icy or so, and then the vehicle is going to work as well. But I think this is potentially not the right way to go. I mean, I'm aware of the fact, and having worked at Toyota Research, we talked a lot about this safety aspect. And if you look at their research agenda, then you see that they are also looking into this space of autonomous drifting, for example. And this is motivated by the idea that in an extreme case, and many, or the majority, not the majority, but a substantial amount of accidents happen because of speeding and cars accidentally leaving the road. And having the ability to actually catch a vehicle in such a situation right? Having a driver assistance system that can catch the vehicle whenever it is drifting on ice or whatsoever, like, would be super powerful. And this is why I think we should also work in these spaces, although the market is not really there, and it's going to be a long time to get this into the market. And this is why potentially there's not so much force in industry to work on these aspects as well. But thank you for this question.
Thank you. Thank you so much.
Thanks for coming.
Thank you.
Yeah.